Hey, everybody, welcome to the next episode of Key Points. On the show today, we have Katie Goetz. Katie, welcome to the show. Tell everyone out there watching and listening a little bit about yourself.
I'm a mechanical engineer. I'm an alum of the University of Maryland. So I graduated in 2018 and I've been with Key Tech ever since. And I recently got a dog. So I'm really digging into that Key Tech culture and bringing a dog to work. And that's been really fun.
Awesome. Yeah, I also remember you're a prolific reader. So, my question for you, I do ask a lot of curveball questions. This one wasn't on the script, but how many books have you read this year?
So I'm actually driving to read 100 books this year. So
Wow.
I'm at just finished 97. So I've got a couple more to go, but I think with the holiday break, I should be able to finish strong. We'll find out.
That that is remarkable. It seems like we need a separate podcast entirely covering the books that you're reading. I guess, are you reading any books related to engineering or product development, or is it purely for fun?
It's
All
totally for fun.
fiction. Yeah,
Yeah, it's all
got it.
fiction. I really use it as like um, a substitute for just watching TV.
Yeah.
So it's kind of, just some junk books, some more serious fiction books, but just for enjoyment. And try to keep it separate from the engineering and the blood and everything.
Yeah. Yeah. So I was gonna parlay your mention of fiction into what I think the topic of today is, which is stranger than fiction. Blood. Our favorite non-Newtonian fluid here at Key Tech. That's a buzzword. You might want to look that one up, folks, if you're on your computer and not listening in the car. Blood. And you actually came to us with this idea from your project experience of blood behaving badly. So
Yeah.
I guess just talk to us a little bit about, what you've been doing. Why are you mentioning blood behaving badly? Just tell our viewership, what you've been doing with blood specifically. Yeah.
Sure. So I've been working on a big project at Key Tech. We're designing a large benchtop diagnostic device. And part of that is sample preps. Imagine you're, at the point of care and you have a sample from a patient, that's whole blood that comes out of a patient's arm. And there's some workflow that goes into making that ready to get any useful information out of. And what that specifically is in this case is lysing the blood. So it's breaking up those blood cells, breaking them open so that you can isolate the DNA from that. So there's been a lot of, interesting fluidics that's come out of that process with this particular fluid because blood is a little bit unpredictable and definitely very different from something like water.
Before the show, you were talking about, you know, this was probably your first project where you were really wading into handling blood, and what you said was, I found it pretty interesting that blood just did not match your intuition when you went to manipulate it. Describe what you mean by the blood not actually behaving like you'd intuitively would have thought.
Right. So I guess when you go into any sort of exploratory de-risking testing in your early design, you have a couple things that you expect to be problematic or things that are going to take more investigating. And I didn't really think that fluidics, like the actual nature of the fluid, would be something that took so much of my time, but it definitely was. And a lot of that comes from blood being, it's a two-phase fluid, which means that there's all these cells suspended in the plasma. And not only is it already a little weird to begin with, but it changes dramatically based on what kind of chemistry you've done to it, what temperature it's at, what speeds it's spun at. And so not only was it different from what I had expected off the bat, but it also changes, like, based on what I was doing to it at the time. So, definitely keeping an eye on the blood was something that became a big part of my everyday thought process during this testing.
So where are you getting the blood? Let's start with that, like this medium here.
Sure.
You're not just collecting your own blood and running tests. I think
No.
that might be illegal. But where are you getting the blood, and describe the characteristics of the blood that are going into your tests?
This is fresh, whole human blood, and there's a vendor up in Massachusetts called Research Blood Components, and they allow you to kind of send in an order form for the type of blood collection you want. So, whether that's fresh whole blood, which is what we're using, just red blood cells, just plasma, that sort of thing. And also, so, when you go to the doctors and you get your blood collected, in that vacutainer, there are reagents that act on that blood in different ways to preserve it or to keep it in a certain state. So we wanted that to also mimic what would be going into the product long term. So in this case, it's EDTA, which is an anticoagulating agent. So it just keeps that blood in n- a nice usable liquid state. So that's the way it comes to me, and then I kind of do on bench in a very, like, sciency manner, some chemical processes that would be done in the assay itself. So that's getting it another level to the state we would expect. So it's not just coming straight out of that tube. There's reagents that, limit foaming, and there's some chemical lysis that's also going on prior to the mechanical lysis.
Are you specifying a certain blood type or, patient age or, and if so or if not, how are you sort of managing the variation of the different types of blood?
Right. So blood is definitely sensitive to each individual person. Like, no two people are going to have exactly the same blood with exactly the same characteristics. But long term, the product's going to have to accept really the wide range of blood. So rather than controlling that, we're kind of controlling to have the full range. So making sure they're collecting from multiple volunteers and we're not specifying anything that would come back to bite us later with some weird variation.
When you run your tests and you get presumably different results, how do you I guess get to the root cause of that variation? Is it to determine whether is it just variation in the blood you're getting or variation in your design or your test bed or the manner in which you're running the test?
Right. Yeah. I mean, it's definitely it's a more intense process to kind of keep track of your testing because it would be really easy to just write off any variations as like, oh, this is just a blood problem. But it doesn't really behoove you to do that because in the long term, if it's a mechanical problem or if it's a test procedure problem, that is going to come back to bite you. So you just have to be very methodical about controlling everything you can so that you can actually have the confidence to say, okay, this one fluidic nuance must just be this blood batch versus our previous blood batch. But that's not something we can really do lightly, especially in early exploratory testing.
So what can you control when you're dealing with what you're describing as a very, stranger than fiction, non-Newtonian input with all kinds of variation? So how can you control the world of your lab testing that you've been living in the last couple months?
So you can be very careful to make sure the blood is being stored in a consistent way from test to test. And then also blood age definitely throws a little interest in there. And what I mean by that is the amount of time from when the blood sample is collected to when I'm using it in testing. And we think that has a non negligible effect on the behavior, at least in what we've seen. So if we start getting weird results and it's blood that I had gotten a week ago, then we decide it's just time to order new blood and kind of remove that question mark from the many differences that there could be in the blood.
Talk to talk to our audience a little bit about, planning for higher volumes and test runs than you maybe have predicted originally.
I guess if you imagine a plastic part that has water in it and it sits around for a couple days, it's not really going to change, the plastic part in any way. There's not going to be like flakes of water that dry onto it. But in the case of blood, that's definitely real. So, blood reacts differently as it's left out in air and we've seen that just on your own body with scabs and we don't want particulates being created and that sort of thing to have an influence on our testing. And then there's also the safety aspect of it. If I have used a prototype with blood, I can't take it outside the lab and do a postmortem on it and see what's going on inside. So it definitely limits kind of what our normal workflow could be. These prototypes never come back to my desk at Key Tech. Like that's not something that's good practice. But then in terms of planning for that, you really, overall, we just want to limit the amount of conflating variables that could be going on there. So reusing a prototype would be one. And that's both from a mechanical perspective. These are disposable coupons we're designing. So they're not designed to be reused, and any sort of cycle testing would be kind of outside of the scope of what we'd expect it to experience in its own lifetime as a part. But then also from the blood perspective, if I were to clean out those prototypes and then reuse them with blood, what if what I cleaned with has some sort of chemical interaction with the blood itself? And that could totally change the way the blood acted.
And then likewise on the chemical side,
Mhm.
what should someone look out for when they're cleaning a intended to be a disposable, but a reusable test disposable, if that's even a thing?
Yeah, so I limit any sort of chemicals at all. So if I am reusing a part and it's going to see blood twice, I rinse with water until it's like visually clear. And that's
Got it.
about all I want to do just because, these are like whole fresh blood cells, and any sort of chemical could change the way that the blood reacts itself, or like the actual chemistry that's happening in there. So there are other reagents in there, and I wouldn't want any sort of, I don't have the science know how to know that it would be fine. So just kind of
Yeah.
avoid altogether.
That's a great segue to our next topic. We work well with our customer
Definitely.
scientific team. So in your case, if you as an engineer are running kind of engineering testing showing that you're meeting certain mixing or flow control requirements, what sort of validation are you looking for from your, collaborative partner on the client side that is like the specialist in the science?
The scientists at our client teams are usually very well versed in these assays. They're doing them on bench in a lab by hand. So they're very useful resources both before and during testing. So before getting protocols reviewed, they can give you tidbits about things that you might not have considered that are really important to control, or things that you shouldn't worry about as much, like, after this step, you can wait a few minutes. If you have to go and set up a prototype, this is a good time to wait. Or after this step, this is not a good time to wait. It's very time sensitive. So they have that kind of first person experience with these protocols to help you kind of suss out things that otherwise you would have just had failures of testing and then realized and, learned from your mistakes. So they've kind of already made some mistakes and learned for you. So that's really helpful. And then also during testing, we're very collaborative with the client team. So I'm able to ping people and say, I just saw this result, send over pictures, send over videos. Um, what do you think's going on? And have that kind of informal back and forth, which really expedites the process of testing, rather than waiting for the next weekly technical meeting and having a more formal presentation. It's able to kind of get that um, quick, feedback, like, "This is something we've seen before, don't worry about it," or, "That's totally new, we should jump on a call and figure that out before you do more tests."
How have you dealt with bubbles in blood management? Everybody's wondering, they're losing sleep at night about these bubbles. It's always on the list of risks. I just reviewed a RFP from a Harvard spinout before this podcast. Bubbles, bubbles. How do they manage the bubbles? So how have you managed bubbles in your experimentation with blood?
So bubbles is a huge part of this particular workflow, and it's not really something we can totally eliminate. Like, it is just part of the way that the blood reacts in this process, and it's not something that we saw with a blood analog. So this is, the foaming was only something we were able to characterize and get comfortable with by using real blood. But yeah, it's definitely, it can add time to our assay, which is our biggest concern at the moment, but it turns out, we're able to pull that kind of more dense foam with a syringe pump just as we might pull with, any other typical fluid. So that was kind of a nice way for the workflow to save us from our bubbles, but there's no way to eliminate them in the actual lysing itself.
So there are a lot of companies, startup companies out there developing diagnostic products. Cardiac care is the largest segment in the medical device market. Heart pumps, ECMO, ambulatory ECMO type platforms, blood going through filters, dialysis. These are huge markets, all centralized around blood and blood
Right.
management. And everybody in this market is pushing to an at-home type platform that's easy to use, that should be easy to use. And as you know, as you miniaturize things, you've worked on, pharmaceutical drug delivery systems in a home environment. As you miniaturize things, like these problems are amplified, um, bubbles, flow control, getting the measurement or moving your fluid kind of very precisely. So, any other like tidbits with managing blood that you might want to share, with folks that are in the entrepreneurial environment trying to prove that product works?
I mean, blood is, as we've noted, a very complex and fickle fluid to work with. So anything that you would normally be worried about in a fluidic system, so channel profile, a channel diameter, having sharp turns, that sort of thing, you want to worry about a little more in this case. So the blood is thicker, and depending on the speed at which you're moving it, its viscosity changes. So any sort of deviations as you're developing a workflow or you're developing a cartridge, you want to keep track of and make sure you know how blood is actually going to react to that change. So it's not necessarily something that you can easily write off as you might with other fluids. Um, Also, just practically, getting blood takes longer time, so there's a couple-day lead time on getting blood from vendors. Anyone who's doing testing needs to be trained, on how to work with blood, how to clean up blood, so there's some back-end stuff as well that, um, is a little bit of a hurdle if you're not prepared early. So, making sure you have all those sort of logistics in place before you get rolling with your blood testing will definitely help you kind of stay in that iterative exploratory testing rather than, waiting several days to deal with the kind of administrative side of things.
So a couple of the questions related to that.
Mhm.
Could you or have you used an analog to blood at all?
Yeah, we used an analog for blood in kind of the early de-risking of this design. And the insight from that is that all the blood analog really did for us was mimic the viscosity. It didn't mimic any other fluidic behaviors. And there's probably multiple blood analogs out there, so it might be more specific to the one we used, but we didn't see this foaming. We didn't really see, um, you're not able to mimic the changes from chemistry. So, adding reagents only really adds volume and changes the composition of the viscosity rather than having a chemical reaction and having that effect. So the blood analog was useful in that, like in some ways, there's less control over where and how we must use it. It can show you just baseline, how is a thicker viscosity fluid going to act, but it didn't give us kind of the whole picture.
Got it. So it could be used probably for early proof of maybe fluidic circuit, but you just have
Right.
to be wary of these odd behaviors that don't match your intuition, as you said originally.
For sure.
Um, in your experience, what is the right framework or approach for, for developing the test, basically? How do you start and iterate as you go through, all the way to the end, like we've talked about, validating what you're getting with your scientific partners?
Sure. So, I guess a great place to start with really any microfluidics exercise is an analytical model. But in this particular case with blood, it does have even more limitations, especially for people who don't have like PhD level backgrounds with fluid dynamics, which I do not. So, you can do a very good job with a pretty simple first principles model to understand the driving fluidics of that system. So, the fluidic resistance of a particular channel, what kind of pressures you're going to get in the system if you're driving at a flow rate, very kind of the simple, highest level of the science. But diving any further into that without doing experimental testing is really kind of an academic rabbit hole. And when you're working in a product design environment, you don't usually have the time or the budget to do that. So you want to quickly kind of move into prototype testing and just doing iterations of that testing. And getting a variety of designs out there for testing right away. So, if you have kind of a core design, but you're unsure about a certain feature or a certain design choice. So, kind of thinking through those higher level design architecture questions instead of doing a lot of theoretical thinking about that, it's pretty quick to just spin things up with like a quick turn 3D printing vendor and then test those in kind of a real application. So that's kind of my next step. And you would want to do that with water or a blood analog first. You don't want to jump right into blood just because there are logistic complications with getting blood. And once a prototype touches blood, it has to be in the lab and that sort of thing. So it'll give you more flexibility if you kind of run checkout testing with, water or a more common fluid first, and then jumping into blood. Maybe you've narrowed down your designs a little bit, maybe you haven't, but the blood testing itself will really give you more information about pain points in that particular design or places where blood is far more sensitive than you expected.
What data are you collecting with, water, let's say? Like, what are you looking for,
Sure.
to help validate that high level model before you start moving into using actual blood? What are you looking for?
Right. So, I mean, it totally depends on the cartridge that you're checking out what you're looking for. But part of what you're looking for is uh, the fluid moving as you would expect. So, staying in nice slugs, being actuated well by whatever method you're using to generate pressure differentiations, you know, and in most cartridges, unless you have an unlimited space, there's going to be turns and serpentines and that sort of thing. And so, is fluid getting caught up at turns or at junctions where you're changing diameter? That sort of thing, And then the more practical, like higher level mechanical things that you're looking for are like, is your coupon actually staying together? Like, are there like physical design things that need to be improved? And doing all that prior to getting into blood definitely makes things easier. So if we had jumped straight into blood, we wouldn't have necessarily known that that was a mechanical problem solely, right? It might have been more difficult to separate out those variables.
Describe how you've used video, or I assume you're using video to, evaluate, your test setup and share results. How are you using video?
Sure. So, yeah, every test I'm doing, my iPhone is set up on a little stand and it is taking video of the entire test. And, that's as much for me as it is for the client. When I want to go back and reflect and, kind of see the nuances that I couldn't see in real time, those videos are an irreplaceable resource for, kind of tracking your testing with as much detail as you could possibly want. I mean, notes and like classic test reports are great, but to be able to go to other engineers on the project and show them exactly what happens expedites that debugging process a lot rather than me trying to recount something. And, human memory is never perfect. So trusting my memory to um, remember every single detail about that test is not really feasible, especially when you're running multiple tests a day and you're trying to um, look for small deviations between different test conditions. Having a video of that test is really important. And also, things that you're looking for in your observations might not align with what the client is looking for at the time. So, you know, I might be worried about things, nuances with my design, and they might be really worried about sound because from a marketing perspective, the sound is, you don't want a very noisy device sitting on someone's lab bench. So you're able to kind of remove any biases about what I'm looking for versus, what someone might be looking for now or in the future.
So you also raised a good point in that response, which is good enough. So describe in your words when you're handling blood in an automated test bed that will ultimately be in an integrated, regulated device. What is good enough for you? Because you're always going to be having these, bubbles or variation in mixing, things like that. How do you know when your design is good enough? To sort of have the confidence to build on, added features before or after, or, take the program to the next phase.
So what's good enough in a de-risking phase is not the same as what's good enough in an alpha phase. So, when you first get that design on the test bed, good enough might be it doesn't fall apart and make terrible noises. But in a few months, everyone's going to want a little bit more than that. um, so it comes back to just like having open communication with your partners at the client side and making sure that you're kind of all on the same page about what you're looking for and what's gating moving to that next step. And if you're working by yourself and you don't have a client, maybe you're a startup, defining those things out front of jumping into the testing will definitely make it easier, to help you not fall into a rabbit hole of trying to run down every little bug, um, that pops up, because especially with working with blood, um, academically, it's a very interesting fluid. Like, me and Ben are one of our other more senior engineers, uh, often saw things that we were like, if we were PhD students, we would want to spend a bunch of time doing testing and figuring that out. But at the end of the day, our success criteria of being able to get that fluid out of the chamber wasn't really affected by that cool fluidic thing we saw. So, it's not something that we needed to run down for that reason.
More specifically, in your case, like good enough would be you've mitigated bubbles, for example, as best you can,
Mhm.
given the constraints of the overall system, and flow control is adequate. The data from the science side is checking out, and you're ready to proceed to the next phase of development.
Right. And
Yeah,
because, at Key Tech, we're not lab scientists, we don't necessarily have all the equipment our clients do. So they do get prototypes from us in this case to do testing so that they can, do post science processing and chemistry to find out actually if the blood is lysing. They're able to run assays that can suss that out. Whereas we can really just see, okay, are we able to recover 90% of the blood that we put in there? That's all we can really say from an engineering perspective. And so we lean on them to get the quantitative results of like performance of that particular design.
sure. Yeah, and that's an important handoff too. I mean, because you
Yeah,
need that insight before you can keep doing more testing or go to the next iteration, design iteration. So
exactly.
awesome. Well, Katie, Key Tech resident blood expert.
Oh,
We'll,
God.
we'll come. We'll come to you. You don't pass out when you see blood, which is
No.
a gift. That's a
Yeah,
gift.
I guess so. It's
Yeah.
very, removed from actual blood for me at this point. It's
Yeah.
just like a red fluid that I'm working with. I kind
Yeah.
of forget sometimes.
Yeah. Awesome. Well, Katie, hey, thanks for your insights today. Super, super helpful. And everybody, thanks for tuning in to the latest episode of Key Points. We'll talk to everybody soon.
Thanks.